and she will be giving a talk on causal discovery using observational data. Welcome.
Thanks for the introduction. Before starting, I would like to mention that most of the result that we are seeing in this talk is a result of the collaboration between Halmstad University and RISE 6 in Stockholm and Halmstad University. And today you are going to hear something a bit different than usual. I want to say that machine learning is not enough. And don't take me wrong, actually, because I'm working in machine learning area, and I pretty much like it. But I see that there is still potential to even evolve it further on. So that's why I decided to give this talk. So we all know that machine learning is good at learning from demonstrations, finding patterns, and also learning from observations, a lot of it. And we see that there has been a rapid development of machine learning, and this field is growing really fast, and it goes toward creating systems that are as automatic as possible. And when it reaches that point, it needs to take certain decisions that needs human intelligence in that regard. What I mean by human intelligence? I'm going to quote Judah Pearl here. So basically, humans have the ability to control and also shape their representation of the environment. And then they distort this representation with the act that we call it imagination. And then they are able to answer questions like what if, that they never heard before. Why this is important? Have you heard, how many of you have seen Groundhog Day's movie? Okay, quite a lot actually. I'm happy because it's a bit old movie. But the good thing about fiction is in fiction we can observe different scenarios that there are sometimes even contradicting with each other. So what happens during this movie, there is a guy, Phil, that he wakes up in the same day over and over again, which is the Groundhog's Day. And he sees that given different action he takes, then he has certain outcome that he can observe. And then the next day he can change his action and see how he can change the outcome as a result. And this is very good, and this is happening in the fiction. But unfortunately, in reality, that's not the case. So in reality, we observe, for example, we have a headache, and after 2 hours, we take aspirin, and after 2 hours, we observe that, okay, I don't have any more headache. But then, we don't know that what was the reason that I don't have a headache right now. The fact that I waited for 2 hours, or taking the aspirin. So what would have been the case if I wouldn't take the aspirin? And there is no other way to measure this. We basically lost our chance to measure the alternative. And these kind of questions are hard. But still, we need to address them. Many of the research questions that we are dealing with in our daily life are causal questions, not correlations. For example, does the death penalty reduces the crime? And if I want to point out the literature, in the literature they try to make a hierarchy of different questions. And they define different levels: association, intervention, and counterfactuals. Starting with association tries to answer questions like what is questions. For example, what does a symptom tell me about a disease? And these kind of questions are usually you can answer either by a statistic or with machine learning, and we are usually very successful in that. The second level of the questions, they are the ones that, for solving them, you need to change something and do some experimentations or interventions. They are, I'm calling them what-if questions. And for example, what happens if we double the price? So you can change something and then measure again, and given this new data set, you can come up with a prediction that what will happen if you double the price. And the third category, which is the most difficult one, there are more about why. And this category is, one good example of it would be, what if I had not been smoking the past 2 years? So you have no way of measuring this data because the past 2 years has passed. So what you can do here is you have to combine the result of the machine learning method that you have with a symbolic representation and interaction with a human. And then base certain reasoning basically on top of it you need to be able to answer these kind of questions. And today, none of the machine learning methods can do this. And that's, I think, where we should go to answer many of these why questions. So how people usually discover causal relation? When people talk about causality, many people actually, they talk about correlation. So one common example in this area is relation between the rain and the umbrella, carrying an umbrella, for example, in London. So, so just by looking at the correlation, there is no way that you can distinguish if the rain is the cause of people carrying an umbrella, or carrying an umbrella is the cause for a rain. It might look a stupid example, but that's the reality. If you have basically two variables and you only know about these two, it's very hard to know which one is the cause, which one is the effect. So, not enough for us to find the causal relations. What else we can do? Many other people, they do intervention. What they do, they say that, okay, let's ban all the umbrellas. But that's too difficult as well. Like, how we can ban it just to test this stupid hypothesis. So, but if we can do it, then it works. But it's too difficult. And many of you are working with A/B testing, actually, and randomized trial. That's usually the more realistic solution in many applications. And the idea is you divide the people in two groups. You will tell half of them that, okay, you can carry the umbrella, and the other half you will force not to carry an umbrella. And then you will measure the correlation of the rain in different circumstances, different population level. That works. That works in many applications. But sometimes it's costly, or impossible, or unethical, especially like in more sensitive application connected to medical care, and so on. So, yeah. So what we want to do? We want to find the causal relations based on the observation data. That's my research goal. But is it possible to do so? Can I really infer causal links from purely observational data? My answer is no. Actually, it's not possible. And that has been proven to some extent. But what I can do with certain assumptions, such as faithfulness, which says that if I find the relation is not accidental. Or considering the conditional independence, if I observe two variables and the conditional relation to the third one, then I can find something called Markov equivalent class of the underlying causal graph. And with Markov equivalent class, I mean, for example, the blue graphs there, they are three different graphs, but they are Markov equivalent. And just using the certain assumption and certain algorithms that, for example, the PERT suggests the PC algorithm, then you cannot recognize between these three. But you can suggest that your causal graph is one of these three. And the one on the left side is the one on the left side is the one that we are certain about. Basically, you can say that if I calculate the conditional dependence between the B and C given A and D, then they become independent. So that's you are certain about. So in this way, some of the links you are certain about, so you can create a causal graph that to some extent you are certain, and some that you are not certain about, but still you can get something out of it. So the definition that Pearls proposes is he defines a graph, and the node of this graph will be variables that we have, and the links between the variables or the nodes will be the causal mechanism. And basically, the parent would be the cause, and the child would be the effect. And the Markov assumption condition in this case would be X will be independent of non-descendant given its parents. So we can calculate this just based on the observation data. Of course, the result we get is Markov equivalence class, not the actual causal graph. I'm emphasizing this because I don't want you to get confused about it. So what are the challenges? Interpreting the result that we get from, which is the Markov equivalence, is hard. At the same time, such causal graphs that we get through these approaches are very sensitive to noise and outliers. Finally, also, when we get something, then usually in real-world application, you don't have the actual causal graph. So you have a hard time to understand the result and interpret the results. But I think it's worthwhile. Why I'm saying so? Because if you ask a right what-if question, then you can find certain directions in this causal graph that you can trust and you can be sure about it. And also, if you evaluate, instead of trying to find the right causal graph based on, in this aspect, this is useful for my application, then you can find the causal graphs that are useful for your applications. So what we are doing as a research is we are working on, we would like to make this kind of bring closer the Markov equivalent class that we find to the actual causal graph. That's the idea that we have in our research environment. So we work on the visualization of the causal graph. We are suggesting a new conditional independent test, and also we use some of the hint in the data to create a causal graph. I will explain each of them with more detail in the next slides. So the first thing that we started to work on was looking at discovering these causal directions incrementally as new data arrives. Sometimes it's hard to collect data or you don't have enough data, but meanwhile you still can get something out of it. So that's the idea. For example, in this simple graph, we use the PC algorithm proposed by Pearl and then G-square measure as a conditional independent test. After a few iterations, we could see there is a correlation between the variables. And that's only the correlation right now. We showed a little bit more data, and then we could find a skeleton of the causal structure. And then when we showed even further data, then we could show that even the direction of the links that we were certain about. And the other directions, we know that there is a causal relation there, but we might not know exactly what is the direction of it. So at the same time also, what we try to do, we try to add uncertainty to our decision. So we find this link, and this has this strength, and we are certain about it with this amount. Basically, this will hint the user that how much they can trust the data. And the next thing that we worked on is we tried to suggest the new conditional independent test to decrease the sensitivity, basically that doesn't require large amount of data in compare to existing approaches. It still is a lot, but less than existing approaches. So I just want to say one thing on it. And the thing is, the method that we are proposing is the extension of the multivariate extension of the odds ratio. And we can also calculate the significance and the strengths for the conditional independence test, like the G-square method that I showed it to you. And then, if we compare this our approach is I-square, with the G-square and Fisher exact test that exist in the literature, then we can see that our method is quite invariant to the percentage of the data that we are showing using for this test. And that's something unique in our approach. And we also did some more tests with different kind of graphs, playing around with a number of variables that we have, and we had to condition on. And in all of them we saw that our approach is the red one, correctly identifies the causal directions and links faster than the other two approaches in all of these graphs. Now, the third thing that we started to work on was, let's look at the data and see if we have certain hints in the data that we can reuse this to improve the causal graph that we have already created using this approach. So we started to look at the clusters in the data. And sometimes when we create, using this approach, a causal graph, we see conflicting links. It means that they are kind of affecting each other, like A, B, and C, they are affecting each other, and you don't know what is cause, what is effect. So what we thought was, probably it should be a fourth variable that we haven't measured, and this variable can explain the relation between these three, but we don't have it right now in our data set. Can we create this variable automatically based on the data? So what we did was we added a latent variable, I call it L, and this latent variable contained the clustering labels of this. If we cluster these three features, if you look at these three features and cluster the data, then I put the cluster label as a new variable to the graph. And then I ran that method, and then we could see that the result got better. So we wouldn't have these conflicting links anymore. And we showed this result in the real-world data set, that also you don't think that what I'm doing is fully theoretical. So here we tested on, we had some data from 6 buses. The data comes from the 6 buses, this data collected in these 6 buses. They are operating in Kungsbacka in Sweden, and they are Volvo buses. And we had 11 signals for these buses, and we calculate the causal relation first on the right without this categorical variable or latent variables, and then on the left we added 2 latent variables. One was idle run, that if the car is idling or not, so it's a binary variable, and the other one is the model year we added. And we saw that actually in the first case we had a strange relation between the ambient temperature and, for example, accelerator pedal position that you don't expect. It doesn't make sense. But after we added these 2 new latent variables, that disappeared. Instead, we had ambient air temperature relation to engine coolant temperature, which makes sense because they are at least we are expecting them to be highly correlated. So this makes sense, but that didn't. So the result got improved, and yeah, we were happy. Basically, this graph, we claim that it's closer to the underlying causal graph. We never claim that it's actual one, because there is no way to measure it. And then, to finalize my talk, I want to show you this comic. Basically, the guy reads the news that Colorado has the lowest obesity level of any states, and he decided to move to Colorado to solve the obesity problem that he had. To me, I wish we could do this, but that's not true. We all know that this is just a correlation, and probably there is a common factor that we haven't measured there. So the lifestyle there is a bit different. I don't know, it's hillier, you have to walk longer distances, I have no idea. But there should be something that we haven't measured, and they haven't had it in that news report. That was it.
Thank you, Sepideh. We have time for some questions for you too. So,
thank you for a really good talk. So, I saw that you added the 2 latent variables in the previous example. How did you decide on these specific variables?
First of all, we looked at the data, the different combination of the features that we had, and we tried to see if we can see clearly clusters in the data. So that was the main motivation behind it. But at the same time also, I was trying to make this more and more automatic. Then you try to basically run certain clustering methods and then pick the ones that has the more disjoint clusters, and then you add the variable. So it doesn't need to be manual. It can be automatic in that sense.
That's interesting. Thank you.
more questions?
Hi, so maybe causality is not my area really, but I was wondering, do you have to pre-specify at least the first model, or your method actually selects all the, so I mean...
So basically the algorithm assumes that you feed in all the features that you need. That's the assumption of that.
You need, or all the features you have?
So you need. But of course, in practice, we feed in all the features that we have. And it doesn't matter. It tries to find, first check all the relations of combination of 2, and then combination of 3 and 4 and 5. So it will check all the possible combinations, then it creates such a graph.
And the latent variable has to be observed?
No, the latent variable you will add it later. So you don't know it when you start. But based on the graph that you
but
get...
it has to be in your data, right?
No.
No, so it can be like an observed confounding.
Exactly, it can be another thing. Even you can create it yourself, so it doesn't need to be in your data set. But based on the graph that you get, you will see that there is something doesn't make sense here. And then you will try to find the variable, define a latent variable that explain why I get certain behavior which I don't expect.
And based on this, sorry, I'm gonna, but this, is the process of also checking that something is not right here automated, or that's the decision you have to make?
That's the decision that human has to get.
Yeah, I would have more questions, but
we can take it offline.
We have time for one more question. Yes.
Thank you for an interesting talk. I have a question on how do you analyze that the result that you get is more correct than the previous one. And as I can see, what you were saying, we are looking at the graph. Do you automate it as well? Because you could apply, for instance, you can check if the paths are shorter or is more clean, or any other things on top of that. Thank you.
That's a really good question. Usually they evaluate the causal graph, they show it to the experts. That's how it works. But sometimes you will see that if I just show it to the expert 2 graphs, they might not see all the links, and they might be interested in certain links, but not the other ones. So it cannot be only based on the evaluation by the expert. What you can do, for example, you can have a new set of conditions, or new, for example, I used 6 buses here. So what if I try for the 7th one? or what if I choose a certain subpopulation in certain conditions and then try to see how many of these links I will recreate using another portion of my data set. So I would say that there are ways to at least understand if what you're getting is reliable, but that's if it's correct or not, that would be the expert to say.
Yeah, I think it's can be interesting, a research problem, another one. Thank you.
All right. Thank you very much, Sepideh, for coming here and presenting. And we, of course, have chocolates for you, too.
Oh, thanks. I love chocolate.
And for the rest of you, if you have more questions, find Sepideh during the break.